what's kind of annoying possibly about this lesson is that some of the problems can be really cumbersome and tiresome, tedious, if you will. But there's nothing really new in this lesson. You've seen these formulas before. Distance formula, midpoint formula, slope formula. You have them on your reference sheet. Just in the interest of thorough note-taking, though, you might want them on this set of notes so that you're not having to refer to multiple sheets. Remember what our distance formula is. x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Midpoint formula is x1 plus x2 over 2, comma, y1 plus y2 over 2. You might do well to make a note to yourself. All this formula does is it finds the average of the x's and y's. Okay, so if the formula looks really weird to you, but you get the idea of how to find the average of two numbers pretty easily, then don't let yourself get overwhelmed with the formula. Just think, let me just find what's in the middle of these x's, let me find what's in the middle of these y's. That's it. Finally, the last formula that this lesson uses is the slope formula. Remember, that's y2 minus y1 over x2 minus x1. And what we're doing in this lesson is taking these formulas from a zillion years ago, way back in chapter 1, and we're applying them to the stuff that we've learned this chapter about parallelograms, rhombi, rectangles, squares, etc. Okay, to clarify, you might want to add a little note to yourself about when these formulas would be used. The midpoint formula is kind of a given. You'll be using it when they tell you you're finding midpoints. Distance formula, however, you're not going to see the word distance anywhere. What you'll use distance formula for is to find segment lengths. And the slope formula we would use to determine whether sides are parallel or perpendicular, or segments are parallel or perpendicular. And as I mentioned, it's not that the problems in this lesson are difficult, it's that they can be tedious and or time consuming, which is why, if you already noticed how short the assignment was, that's why. Okay? So notice that in problem 1, we're classifying this triangle as scalene, isosceles, or equilateral. Let's refresh our memory on that vocabulary. What does it mean for a triangle to be scalene? Right, none of the sides will be equal. How about isosceles? What does it mean if the triangle is isosceles? It has two congruent sides. And then finally, if the triangle is equilateral, then all three sides will be congruent. So, I started off this lesson by giving you 3 formulas, or reminding you of 3 formulas. Which one do you think we're going to use here? The distance formula. We need to find the length of these segments in order to decide whether any segments are congruent. So let's first identify the coordinates of these points. R is at negative 4, 1. And please correct me if I misidentify a point. It's kind of hard to see it from this close. The strings that we see. 3, 3. And 1, -3. So here we go. Our S is 1 minus 3 squared plus negative 4 minus 3 squared. simplifying. Of course, you remember that when I take this -2 and square it, it becomes positive. Same thing with this -7. When I square it, and since the actual length of the segment is not what I'm interested in, but rather whether I have segments of equal length, just stop here. There's no reason to figure out what the square root of 53 simplifies to. Okay, let's stop there. Moving on to the next segment, ST. 3 minus -3, or 3 plus 3, squared, plus 3 minus 1, squared. So this is 36 plus 4, or the square root of 40. Do we have an isosceles triangle yet? No? So far I got buckus. That's an old person word. RT, last one. 1 plus 3 squared plus -4 minus 1 squared. Taylor, you still with me? 4 squared gives me 16 plus -5 squared gives me 25. So that's the square root of 41. Like I said, it's not that it's difficult, it's that it's tedious. All of this for one little word. So what's the word? It's a scalene triangle. In the interest of time, I know I have some of your turns. I put them there just in case we did have time, but I want to get through the different problems first. Questions on this kind of problem? Okay. Still getting from the screen what you need. Right. In problem 2, we're being asked if this parallelogram is a rhombus. Now let me point out something to you that is tremendously wonderful. The fact that they've already told us that this is a parallelogram is very helpful. Okay? But I need to ask myself, is it more than this? So like I said, it's not that we're doing new things, but we're taking old things and applying them to this chapter. So let's think back on this chapter. What do we know about rhombi that I could use one of those formulas to determine whether this is a rhombus? Well, let's backtrack. What is a rhombus? What's a rhombus? What makes a parallelogram a rhombus? Come on, think about it. Catherine. All congruent sides. So I could go through and use the distance formula 4 times and see if those 4 sides are equal. Anyone got a better idea? There's a better idea out there. What? Oh, yeah, we looked at those 3 formulas and, oh, slope is the nicest one. How could I use slope in order to determine whether this is a rhombus? Yes, ma'am? Absolutely. Remember that in a rhombus, the diagonals are perpendicular. So if I can calculate the slopes of these diagonals, show that they're opposite reciprocals, I'm done. All right? So, slope of AB. Once again, let's start by identifying all of our coordinates. This is -3, -4. Well, I'm going to go all the way around. C is -2, 3. B is 5, 2. And D is 4, comma, -5. You good? So far? All right. Now let's find that slope of line AB. That gives us -4 minus 2 over -3 minus 5. Since I have negative on top and bottom, I know negative divided by negative is positive, so I can just write 6 over 8, and that reduces to 3/4. So that looks like. Next, we find the slope of the other diagonal, CD, and that one is 3 plus 5 over -2 minus 4, and that gives me 8 over -6, which reduces to -4/3. So, are these diagonals perpendicular? Yes. Is this a rhombus? Yes. And that was nowhere near as annoying and dreadful as finding the lengths of 4 segments. As far as explain, all of this is how we explained it. Still not so bad? Yes, ma'am. I would really, myself personally, I would guess that the absolute worst, dreadful problem that the EOC would have might be more like problem 3, which is even less attractive than this. It took me 2 boards during first period, just on problem 3. You only have one of those in your homework, by the way. Okay. You ready? Crack your knuckles. Here we go. Okay. And to answer your question, Sarah, is it feasible that the EOC might have a question like this? I would say probably. However, do keep in mind that when there's standardized testing like the EOC, like the FCAT, like other stuff, a lot of times they throw questions on there just in the interest of, I wonder how we'll do on this. But it's not actually assessed as part of your score. Okay? It's kind of experimental question. Always do the best that you can on any question, though. Okay. So, in problem 3, we're being asked to classify the quadrilateral formed by the midpoints of the sides of this trapezoid. So, like I said, really the only time you're dealing with midpoints are when they're telling you you got to deal with midpoints. So, 2 of the midpoints are really easy to find. We can just count the boxes on those 2 horizontal segments. All right, in the interest of being able to refer to those midpoints in a concise way, I'm going to name them W, X, Y, and Z. Okay, so here's W, located at 0, 3. X is going to be the midpoint of an M. Y is another nice, pretty point that I can just count the spaces to find. Y is here at 0, -2. I'm sorry, I labeled it. Sorry. But X and Z require a little bit more math in order to find. You can use the midpoint formula. Remember, that's the average of the X's and the average of the Y's. Or, since it's on a grid, you can kind of visualize where halfway is. Okay, so in this diagram, we see that X is there. What do you think the coordinates of X are? Based on where we see it. What do you think the coordinates of X are? realizing that it's halfway between the x's for m and n, and it's halfway between the y's for m and n. X is located at 3.5, comma 0.5, and Z is right there at negative 3.5, comma 0.5. All I've done so far is find where the midpoints are. Now it's asking us to classify it. So, any thoughts on what we can do with those coordinates in order to classify that quadrilateral? What's your formulas? How would you use your formulas in order to classify this quadrilateral? What formula would you most like to use? Not the distance formula. I mean, you could absolutely use the distance formula and find the length of all 4 segments. But again, myself personally, I think slope is the easier one. Now, the slope of, think back to problem 2. Think about how we used slope in problem 2. We found the slopes of the diagonals, and we found that the diagonals are perpendicular. Look at these 2 diagonals, though. You see that this is a vertical line, and this is a horizontal line? Can we kind of glance over the idea of finding the slope and just realize, oh, a vertical line is perpendicular to a horizontal line? So right now, I know that my diagonals are perpendicular, which means this could be what? Could be a rhombus. What else could it be? Could be a kite. Anything else it could be? Yes, it could be a square. So, oh, that's not what I meant to do. In the interest of time, space, and the fact that we actually have this graph, I'm going to glance over kind of what we did in first period and make this a little bit easier to process. Okay? What we did in first period, very, very tedious. Benjamin's already falling asleep just thinking about it. It's all right. What we did was we found the slope of Wx, and we found the slope of xy, and we found the slope of yz, and we found the slope of wz. Tell me what your gut instinct says that this is. What's going to be the same? Of all of them? The slopes of, yes, wz and yx are the same. The slopes of zy and wx are the same. Whoa. In order for it to be a square, now what we've noticed, if I just and remember, because this isn't a diagram, remember what you are allowed to do. Remember what your teacher last year allowed you to do when you were finding slope. Remember, count the rise, count the run. You can do that here. It's okay. So let's do that. If I count my rise from z to w, do you see that I'm rising 2.5? You see that I'm running 3.5. With me? Okay. Let's look at yx. Once again, do you see that we are rising 2.5, running 3.5? All right. So by that token, I know that wz is parallel to yx. And as I was writing that, I'm hoping some of you were kind of already looking at wx and zy and realizing that their rise over run is also the same. But here's my question to you. In order for this to be a square, the adjacent lines would have to be opposite reciprocals. Did you happen to notice whether they were? Let me say it again. From Z to W, notice our rise, notice our run. I'm rising 2.5, running 3.5. Let's look at WX. For WX, I'm rising -2.5 and running 3.5. Are they opposite reciprocals? No. They're opposites, but not reciprocals. Okay? So my opposite sides are, WX is parallel to ZY. And when I put those three facts together, the fact that I've got two pairs of opposite parallel sides, my diagonals are perpendicular, what is this? The rhombus. Remember, a kite is not a parallelogram. What you need to observe is that these parallel lines tell us this is a parallelogram. Okay, so this is a rhombus. So I tried to make this a little less painful than it was in my first period. Are we okay though? You see, you only have one of these in your homework. You're welcome.
You would have one of them on the test, or possibly none?
Yeah. I actually had a good question. I had one of these on the space race review, and then after doing it first period, I pulled it. But I am telling you, there's other stuff from today's lesson on Monday's test. Okay? So, we are done. There is a